Hi guys. Okay, so let's look at this chapter on acids and bases. This is chapter 11. So in this video, we're going to look at what are the acids and bases, their definitions and their properties. Then we'll look at the naming. Then what are the monoprotic acid, diprotic acid, and triprotic acids, and then the strengths of the acids, the strong and the weak acids that relate to the electrolytes, the concept of electrolytes. And then we will look at the Arhennius view and the Bronsted-Lowry acid-base, theory, acid-base, this is a theory. And then the last is the conjugate acid-base pair. And if there is time, we will look at the direction of reaction and the dissociation constant of acids, if there is time. Okay, so let's get started now. So here we have the acids and bases. First of all, what are acids and what are bases? So acids are those substances that liberate hydrogen ions, and bases are those substances that liberate the OH ions. So hydrogen ion donors and OH ions donors. Okay, that's the base and the acids. Next is, that means that the acids are also proton donors. Acids donate protons, and bases, they accept protons. So they accept protons. On the other hand, acids accept electrons. So they accept electrons. Let me put this here. Accept electrons, and the bases, they donate electrons. So they are the let me just put this here. Okay, so I have just changed it here. So they donate protons and accept electrons. That's the acids. And the bases, they accept protons and they donate electrons. Next is the taste. The acids are obviously sour in taste, and the bases are bitter in taste. Next is the acids are also corrosive, means when they, if they fall on your skin, then they are going to cause like the burn on the skin, which is going to be very deep. Bases are also corrosive, but the kind of burn that they produce is more like, it more spreads out. So it's not localized, but it's more like, upper surface, but more spreads out. Okay, so both of them are corrosive. Now, next is the acids. The pH of the acids is less than 7, whereas the bases, the pH is more than 7. Okay, now that is the pH is an indicator which tells us how many hydrogen ions are there and how many OH ions are there. So OH ions is more, so in the base, so it's more than 7. And pH ions are less in the acids. The OH ions are less in the acid, so it's less than 7. Okay, next is the also there is an indicator called phenolphthalein. Phenol, pH, phenol, I don't know the spellings here. Phenol, let's do this here. Phenolphthalein turns pink in the presence of a base. Okay, so that is an indicator, because see, here's the thing, both of them are colorless, right? But how do we know which one is which? So if you put phenolphthalein, which is an indicator, then phenolphthalein will turn pink. And if that turns pink, that means the solution is basic. But here, phenolphthalein has no effect. Phenol, P-T-H-A-L, and it remains colorless. Okay, so that pink color tells us. Okay, so we will study more about the acids and bases in this chapter. Next, let's look at the nomenclature of the acids and bases, naming and writing the formulas. So nomenclature, and in this nomenclature, we are also going to look at the names. We are going to look at the formulas. And here only, I am looking at the mono, di, and triprotic acids. Okay, So let's look at, first of all, the acids. And these acids, the ones that are monoprotic. Monoprotic means mono. Mono is one. Protic relates to protons. So that liberate only one hydrogen ion. Okay. So first of all, let's look at the nomenclature when there is hydrogen and fluorine attached. Okay, if it is an acid, then it is the name, so it will have this AQ added to it, means in the aqueous medium, that means in the water. Similarly, HCl, aqueous means water. HBr, aqueous, water. HI is again in the water medium, aqueous. So here the name is hydro is common to both of them, to all of them. Hydro is common to all of them. Hydro. So this becomes fluor, F-L-U-O-R-I-C, hydrofluoric acid. Hydrofluoric acid. Okay. This becomes hydrochloric acid. This becomes hydrobromide acid. Then this is hydroiodic, and then you have dic acid. Okay, so all of them have one thing common. Hydro is written in front. Ic, they are ending in ic, and then the acid. Okay, so these are the common things depending upon what it is: fluorine, chlorine, bromine, iodine. So that's one thing. So these are called a monoprotic, means they will give one. But there's another thing, nomenclature, that is associated with them. If HF is in the gaseous state, then this becomes hydrogen fluoride. So that's the difference in the names of these molecules, HF, HCl. Similarly, if this is in the gaseous state, then it's hydrogen chloride, IDE is there. Then if it is HBr in the gaseous state, this becomes hydrogen bromide, IDE. Then if it is HI in the gaseous state, this becomes hydrogen iodide, Okay. So that's only in the gaseous state. So keep this in mind, that this is in the aqueous medium, means in water. And this is in the gaseous phase. So in water is aqueous, in gaseous phase is gaseous phase. So then it will be G. The name is ending in ide, all of them, because it's just a single non-metal, and then hydrogen is common to all of them. Okay. All right, so that's the deal with these guys. Besides that, the other monoprotic acids, you just have to memorize their names now. Memorize their names. Memorize their names. How would you memorize their names? All right, these guys, for example, HNO3. This is nitric, NITRIC, nitric acid. On the other hand, if you have HNO2, then this is nitrous acid. So lower oxidation state is us, higher oxidation state is ic. Lower oxidation state means with the oxygens. Lower oxidation state is ending in us, and higher oxidation, let me put this on top, higher oxidation state is ending in ic. Okay, So keep that in mind. Is related to the number of oxygens that are attached. Okay, so higher is ik, lower is us. So here we see 3 oxygens, ik, 2 oxygens is us. All right. Now, besides that, there is also other types of names, which is like, say, for example, this guy, H, CN, HCN, HCN. This just has this thing. So this is, the name is hydro, just like you have hydrofluoric and hydrochloric. So this is hydrocyanic acid. Okay, so hydrocyanic acid. The only thing, the name of the anions, is the CN is just one, anion. So that's the name. So you have to memorize this. Okay. Now, other types of names. For example, now these are the other special names which you have to just memorize. Special names for these monoprotic acids again. For example, HClO4, HClO3, HClO2, and HClO. Okay, so HClO4 has ClO4 anion. HClO3 is HClO3 anion, ClO2 anion, and ClO anion. Okay, so that's one thing. Next is the name of first, this was discovered and then this was discovered. So the name, this one becomes chloric acid, chloric acid, only because this was discovered first. After that, the other guy was discovered lower oxidation state. They said, fine, okay, chlorous acid, chlorous. So this is how they got their names first. But later on, as more and more, chemistry evolved and new things got discovered, then they discovered, wait a minute, chlorine can also form ClO4 anion and ClO ion. So how do we name them? We can't change the names of chloric and chlorous now. Although HClO4 is the highest oxidation state, then what do? So then the name becomes per, like hyper, so this is per chloric. So I'll just put it here, per chloric acid. And the lower one is perchloric acid, and the lower one is hypochlorous acid. So lower than chlorous is hypochlorous, and higher than chloric is perchloric, like hyperchloric. Okay, perchloric. So this is how you name these guys. Okay, so it all depends. So this is our special names, per and hypo. So this is coming from there. The rest of the stuff is still the same. The higher oxidation state is ik, and the lower oxidation state is us. The lowest of the lower is hypo, and the highest of the higher is the perchloric. So this piece is still the same, chlorous and chloric. Okay, all right. So next is we are going to look at the diprotic acids, the naming in the diprotic. So the naming of the acids in monoprotic acids. Now acids, we will look at the bases also, acids that are diprotic. Diprotic means that they are releasing 2 hydrogen ions. Okay, so they will release 2 hydrogen ions, and we will look at how they release and all that. So diprotic is releasing 2 hydrogen ions. All right, so we have here now, in this case, for example, same story, H2SO4 versus H2SO3. Okay, so the name is because the anion is sulfate anion -2, and this one, the anion is sulfite anion. So this is a sulfate polyatomic ion, and this is the sulfite. Sulfate. Yeah, sulfite. Okay, so this becomes sulfuric acid, and the other one is sulfurous acid. So this is sulfuric acid, and this guy is sulfurous. Sulfurous acid. Okay, so two things, sulfuric and sulfurous. Okay, so now we have these are the diprotic. Now let's look at the other acids, which are also well, actually we'll look at their the organic acids later. Let's look at other acids that are triprotic. So acids that are triprotic means they are going to release 3 hydrogen ions, or they have 3 hydrogen ions. So if you look at it here, 2 hydrogen ions. Okay, so same is the case here. Let me just put this another color. So all of them are releasing 1 hydrogen ion. If you look at here, 1 hydrogen ion is right here. All of them have 1 hydrogen ion. All of them, these guys have 1 hydrogen ion. All of them have 1 hydrogen ion. All of these guys have 1 hydrogen ion. You see that? Okay, but the other ones are this one is 2 hydrogen ions are right here, 2 hydrogen ions. Okay, and the rest, the naming is ic and us is coming from how many anions are there based on that. Okay, so now we have the triprotic acid. Triprotic acid will release 3 hydrogen ions. Okay, now these 3 hydrogen ions are, for example, the names of the acids are H3PO4 and H3PO3. So once again, H3PO4 made up of phosphate anion, and this is phosphite anion. Okay, so the name is, this guy will name is going to be phosphoric acid, phosphoric acid, higher oxidation state, and the other one is phosphorus acid, lower oxidation state. Okay, phosphorus acid, lower oxidation state. So once again, 3 hydrogen ions are here, and the rest is, you will see the nomenclature based on phosphate is giving it ic, phosphite is giving it us. Okay. All right, so these are the mono, di, and tri. Now let's look at some of the organic acids. Now, organic acids, again, it's, you just have to memorize their names. That there's just no way you know, that's the way it is. So organic acids, and these are, they can be mono, di, tri, whatever. They can be mono, di, and tri, and so forth. So you just have to memorize their names. There's no particular, you know, way. I mean, there is an order where they use the IPAC naming, but let's look at this now. For example, here is this C. Wait, let me just put it on a separate page. Okay. All right, so here we have C, H3COOH. This means C, H3, H, C, O, H. So there's one thing important is this group. This is the acidic group. Okay, this acidic group, this is called the acidic, like this set of atoms arranged in this way. This is called the acidic group, and this acidic group is what makes this is called a COOH. And with that, this is the acidic hydrogen. These are non-acidic hydrogens, non-acidic. Okay, in other words, this hydrogen is released as a hydrogen ion. So this hydrogen, acidic hydrogen, is made into hydrogen ion, released as a proton. Remember that this whole thing is called proton. So the hydrogen ions are also called protons. Okay, so this hydrogen ion is released, and that is what makes the acid. The acid, like this is what makes this molecule acid. And what is the name of this? This is called the acetic acid, ACETIC, acetic acid. And this acetic acid is vinegar, which you see in your kitchens, vinegar. All right. Okay, so now because it's releasing only one hydrogen ion released, so that is why this is a monoprotic acid. So no matter how many hydrogen ions are there, hydrogens are there on the other hand. Look at this example, CH3, then comes CH2, then comes CH and H, and here is COOH. So this is still a monoprotic acid. Why? Because these hydrogens are non-acidic hydrogens, and only this hydrogen is acidic. Okay, so this hydrogen is acidic. But all of these are non-acidic, means they are not going to be released as hydrogens. So non-acidic hydrogens. Acidic hydrogen is the one that is capable of forming hydrogen ions. Okay. So with that said, yeah, this is also a monoprotic acid because it's releasing only one hydrogen ions. Now, on the other hand, if you have an acid which looks like this, so this is one example, this is another example, and then comes the third example. Like, for example, you have C in a ring, C, and this. Okay, and you have, sorry, let me just put it here, COH. Okay, this is CH, 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 CH. So this is all these hydrogens in a ring. Okay, so no matter what, this is the acidic group, and that hydrogen is the acidic hydrogen. The other hydrogens are tied up in the ring with these carbons. So they cannot be liberated. Okay, so again, this is called, the top one was 1, 2, 3, 4. The top one, the name was butanoic acid. So this is butanoic acid. Okay, and this guy over here is called benzoic acid. Benzoic acid. And what's the deal with the benzoic acid? Benzoic acid is only one hydrogen ion, only one hydrogen liberated as hydrogen ion. So therefore, this is also monoprotic. All right. All right. Next is, we are going to look at let me just give you one more example. So here is COOH, 4, and then other one is COH, and let's put this here. So this is carbon-carbon double bond, no, carbon-oxygen double bond, carbon. So this is oxalic acid. This acid is oxalic acid. So this is oxalic. So you must have heard the name oxalic acid. Okay, again, organic chemistry, you have to memorize this. So just so you know. Okay, this case, OH, you know, so there are two of this is going to liberate. So these are, this is because it's attached to OH. This is attached to OH. So this hydrogen is acidic. This one is going to be released as the hydrogen ion. Okay, so this is a diprotic acid because it can release two hydrogen ions, diprotic acid. All right, so this is just so you guys know. So next, let's look at, now we got the naming covered. Now let's look at the naming of the bases. How do we name the bases? So bases, again, it depends, you know, how many hydrogen OH ions are there. So based on that, we just call them hydroxides. Hydroxide are, you know, the OH ions. And so we have, like, for example, sodium with OH. So in other words, metal comes first and then comes the hydroxide. That's how you name them. So this becomes sodium hydroxide. This becomes magnesium hydroxide. So do not use, in this case, di, tri, tetra, and so forth. Okay, so we just have magnesium hydroxide. You have aluminum, 3 hydrox OH. This is still going to be aluminum hydroxide. Aluminum hydroxide. Now, if you have something like this, which is lead, right? Let's just, this is writing big. Pb, OH, whole twice, and Pb, OH, whole thrice. So this becomes lead 2 hydroxide. The other one is lead. Oh, sorry, it's not 3, it's 4. Lead 4 hydroxide. All right. So that's how you give their names to the bases. Now, all these bases are releasing, remember, the hydrogen ions, but there are also electron donors are also bases. Electron donors are also bases. So we have, for example, ammonia. 2 lone pairs on the top and hydrogen, hydrogen, and hydrogen. Right here. So that's the structure of ammonia. And this is, the name is ammonia. Okay. And because it has these lone pairs on the top, so ammonia can also, these lone pairs are donated when needed, are donated when needed. Therefore, ammonia or NH3 acts as a base. NH3 acts as a base, electron donor. Okay. So this is one thing. Now we are going to look at, next is the, so this was the acids, acid base, this is the properties. So number 1, properties of acids and bases. Number 2 is the nomenclature. We covered nomenclature in extent in quite a big, extent. So in the nomenclature also, we looked at the monoprotic, then we look at the diprotic, then we looked at the triprotic, then we look at the organic acids. Organic acids. And then we have the second, this is the nomenclature of acids. Okay, 4 bases, hydroxides, and 5 is the electron donors. Okay, next is, now we have the strengths of the acids and bases. Now, how do they, dissociate? So let's look at now the third part is the strengths. So in other words, strong and weak. Strong and weak. Okay. So here's the way, this is how they are going to dissociate. First of all, let's look at the acids. Okay, so here we have HCl, aqueous medium. The moment HCl as a gas is bubbled in water, okay, this is going to give you hydrogen ion, aqueous, and chloride ions, aqueous. And this is all in a aqueous medium, means in water medium. So acids in water. So this is 100%. This is 100% dissociation. Dissociation means in one step. Okay, so this is a strong acids. Okay, so these are, let me just put this here. So this is a strong acid. If it's 100% dissociation, okay? But on the other hand, you have H2, or let's look at this also, HNO3, aqueous medium. When it breaks up into hydrogen ions, aqueous, and the nitrate ions, aqueous, okay? And so this is again 100% dissociation. Dissociation is breaking up into ions, okay? And in one step, this happens. So this also is a strong acid, or we can say just the strongest, among the strongest acids. So very strong acid, very strong acid. Okay, so this is in one step. Okay, next is the example with this guy, H2SO4. H2SO4 aqueous breaks up into first as hydrogen ions, aqueous, plus HSO4, 1 negative, and that's aqueous. After that, 1 HSO4 breaks up into hydrogen ions, aqueous, plus sulfate ions, SO4, 2 negatives. So this is 1 negative, and that's aqueous. So this is in two steps, dissociation occurs. So it is a strong acid, but it's comparatively releasing hydrogen ions slowly. So in 2 steps, dissociation occurs. So it is not very, it's a strong acid, but it's not very strong as compared to. So in comparison to monoprotic acids, monoprotic means all of them, the ones that monoprotic inorganic acids, not the organic ones. All organic acids are weak acids. Okay, monoprotic inorganic acids, H2SO4 is less strong, you can say. It is strong, but less strong. So HCl is more than H2SO4. That's what it means. Okay, although it appears that there are two hydrogen ions. So two hydrogen ions are released, two hydrogen ions released slowly. And here the one hydrogen ions, so one hydrogen ion released quickly. That is what it makes this very, very strong acid. Okay. All right. Next is, let's look at this guy also. And that is H3PO4. What happens in that case? H3PO4, how are these hydrogen ions released? H3PO4 aqueous will release it in 3 steps. First, one hydrogen ion released, aqueous, and we have H2PO4, 2 negative. And that's also aqueous. Okay. Then H2PO4 will break up into hydrogen ion, aqueous, and it gives you HPO4, 1 negative, sorry, yeah, 2 negatives, yeah, 1 negative, and aqueous. Okay, and then you have this guy then giving you hydrogen ions, aqueous, and PO4 minus 3 aqueous. So all the 3 hydrogen ions have been released. Phosphate gets 3 negative charge. Oh, sorry, this is, I made a mistake here. That's what I was thinking, something is off. So this is going to be minus 2. Sorry, this is minus 1. This is minus 1. And this one is minus 2. And then becomes minus 3. Okay. So now, so in that means in this case, 3-step dissociation. And in a 3-step dissociation means that 3 hydrogen ions are released slowly. Okay, therefore, so if you compare, so it's a slow dissociation. So here we have now, first come HCl, that gives away a lot of its hydrogen ions in 1 step. Then comes H2SO4, which releases 2 hydrogen ions in slowly. And then comes H3PO4. I mean, all of them are strong acids, but it's not that how many hydrogen ions are present, but it is how quickly those hydrogen ions are available. Let me write this down. So it is not the number of hydrogen ions present in the acid, but how quickly these hydrogen ions are released that determines the strength of the acid. Okay, strengths of these acids. All right, so same is the case. For the bases also, same story. We will have the bases. So this was the acids, and that's 2 bases. And now in the bases, we will see that they release hydrogen ions, release OH ions, So same story. not the total number of hydrogen ions, but OH ions. But it's like, for example, you have NaOH. NaOH is very strong base. Very strong base. Why? Because in one step, 100% dissociation. 100% dissociation, and you will have sodium ion plus OH ions. Okay, sodium ions are aqueous and the OH ions are aqueous. So in a single step, you know, they are released. And 1 second, I am not sure about the other acids, or the other bases. So let me just look at it. 1 minute. Okay, so we see here that sodium hydroxide is going to release all of the OH ions in one step. Now, look at the trend in the periodic table. When you go down the group, in the same group, when you go from top down to bottom, from top to bottom, the basic character increases. So in other words, top to bottom, the basic character is increasing. Increase in basic nature. And when you go in the same period from left to right, in the same row, and here the same group. So you see there is a decrease in basic nature. So this is, you know, you will study this more in the next thing, but for now, suffice to say that there is lithium hydroxide, then there is lithium, sodium, potassium, rubidium, cesium, and francium. Okay, so we would see that this is increasing. So we would see that the sodium hydroxide is more basic than lithium hydroxide. Potassium hydroxide is more basic than sodium hydroxide, rubidium hydroxide, and so forth. But the thing is that this is more commonly used. This is more common. These two guys are more commonly used. Okay, more commonly used. So therefore, we call them, like, you know, quickly OH ion is released. So we call them it's a very strong base. Okay. On the other hand, you have other guys like magnesium hydroxide, calcium hydroxide, barium. So here I have, let's just write this down here. Magnesium hydroxide is giving you 2 OH ions. Then aluminum hydroxide is giving you 3 OH ions. And similarly, let us say you have lead OH whole 4. So this is giving you 4 OH ions. Okay, so this is magnesium plus 2 charge and 2 OH ions. And these are in aqueous medium, all of them. This one would give you 1 aluminum ion with 3 plus charges and 3 OH ions, right? And this is again aqueous medium. This one is lead plus 4 state, aqueous, and 4 OH ions, negative charge, aqueous. Okay, so this is the way they dissociate. Okay, so the more the OH ions are, yes, it is going to be basic, but just keep this in mind that how quickly they are released, that also determines their strengths. Now let's look at the next concept, which is of Bronsted-Lowry acid and bases. So we have now the Bronsted-Lowry acids and bases. Arhennius. So this is basically Arhennius concept. What we covered here is the, give me 1 minute, 4. So this is Arhennius view, this dissociation. So Arhennius said that, when the acids dissociate, so Arhennius theory came up with the concept that hydrogen ions are released and the anion of the acid is released. Same is the case. He also said that when the bases, they dissociate, they release OH ions, and then the metal ions are also released. Okay. But Bronsted said, so this is part, sorry, this is 4. Okay. Now, Bronsted, B-R-O-N-S-T-E-D, Bronsted and Lowry theory. They said, okay, wait a minute. We understand hydrogen ions are released, but they are not just floating around here and there. So what is happening? They said, okay, this is the true picture. Here is the water molecule. I draw this here. Water molecule. They looked at the electron donors and the acceptor situation. So electron donor and electron acceptor scenario. Okay, so what's happening here? So it's not just OH ions and the hydroxide ions, but in the aqueous medium scenario, in aqueous medium, what's happening in water, basically. Okay, now, so we see this is the water molecule. These are the 2 lone pairs on oxygen. And here's this HCl, which is a very polar bond. Okay, so already we see this being a polar bond. Chloride has a positive charge and the hydrogen has a delta positive charge on hydrogen and a delta negative charge on chlorine, because this is a very polar bond. Okay, so this polar bond, due to this polarity here, we also see the polarity in water molecules. Hydrogens are positively charged, oxygens are delta negative charge, small charge, because the electrons are more towards the oxygen, because oxygen is very electronegative. Here chlorine is electronegative. So because of that, yes, this is also, there is a polarity in this molecule also. This is also a polar bond. So polarity here also. Okay, but oxygen has a power. Oxygen has these lone pairs. So what does oxygen do? Oxygen then lends its lone pairs to this hydrogen. Because this hydrogen is delta positive, means less hydrogen, less electrons on hydrogen. So oxygen gives its lone pairs to hydrogen and this bond breaks. So this is how the electrons, they move. So when these two are mixed together, what we see now is a structure like this. This hydrogen ion, this hydrogen is still intact. This bond doesn't break, but a new bond is formed with the neighboring hydrogen, which is actually called the coordinate covalent bond. And oxygen gets a positive charge, because it has given its lone pairs to the neighboring hydrogen. And when that happens, now we see that this chloride ion is liberated. And this chloride now has a full negative charge. Delta is just partial charge, little bit of the charge, partial charge. But chloride has a, negative charge, and we have this guy. Okay, what is this called? This is called hydronium ion. Hydronium ion. And this is, of course, the anion, which is the chloride ion. Okay, so hydronium ion is also expressed as H3O plus charge. All right. So this is what they said, that in the acidic medium, hydronium ion is released. And anytime you see this hydronium ion, that thing is acidic. Okay, so this is the deal with the with this guy. But what happens in the bases then? How does this happen in the base? So this story is with the acids. And now we're going to look at it in the bases. How does this happen in the base? So now let's look at the scenario. Same story, because we are looking at the acids in water and the bases in water. So here is this ammonia, lone pairs, and 3 hydrogens. Okay, now what we see is same story. We see nitrogen, so again, nitrogen is more electronegative. Okay, and same story here, oxygen is electronegative. So this is going to be a polar bond. This is also a polar molecule. Okay, nitrogen has a delta negative charge. Each of the oxygen or hydrogens here have a delta positive charge. This is delta positive, this is delta negative, this is delta positive. Okay, now what happens in this case is that this nitrogen, in this case, oxygen does not. Oxygen has a lone pair, nitrogen also has a lone pair, but nitrogen lends its lone pair to this hydrogen and this bond is going to break. And when that happens, when these two are mixed, then what happens is that we will see a structure that looks like this. So these 3 hydrogens of nitrogen remain intact. They don't go anywhere, but a new bond is formed with the neighboring hydrogen. And actually, now this one gets a positive charge. This is a positive, full positive charge. So this, and what is released here is the OH ions. So OH ions are in situ generation. In other words, internally OH ions. So this is the OH is released and we have a negative charge on this. Okay, and so the way we write is OH negative. The charge is actually on oxygen, but we write it like that. And what is this called? This is called ammonium ion. Ammonium ion. And this is NH4 plus. And this is hydroxide. Hydroxide ion. All right, hydroxide ion. So that's the Bronsted-Lowry acids and base. So this is what makes the acids. And this is what makes the base. So we see that the acids will always have hydronium ion. And anytime the base is there, no matter where, ammonia doesn't have the OH ion, but it has generated the OH ion. So anytime you have the OH, this is called the in situ internally, in situ generation of OH ions. So it's not a direct, it's an indirect base. So this is acting as a base. So this is basic in nature. Okay. So we will see that water can also react to itself. But now let's look at this conjugate acid-base pairs. Okay, 4 and then 5. Conjugate acid base, conjugate acid and base. Okay, so today, I'm just going to end at the conjugate acid. So we are not doing the direction of the reaction. This is going to take longer, but we will visit this again when I do the next conjugate acid-base pairs. Okay, so this is the last we'll do in this. So now here, conjugate acid-base pairs. Keep this in mind that every acid has a conjugate base. Every base has a conjugate acid. All right. But then what's the difference? The difference in the two, difference, D-I-F-F-E-R-E-N, difference is of one hydrogen ion. Let's look at this example. So you have one example here, one example, HCl. So when HCl splits up, HCl is going to break up. So HCl is an acid, okay? And when it splits up, it gives away minus one hydrogen ion, and it gives you a chloride ion. And this chloride ion is the conjugate. So I'm going to here, conjugate base is Cb, and conjugate acid is Ca. Okay, so this is the conjugate base of HCl. You see that? It's a difference of one hydrogen ion. Let's look at this one. HNO3. HNO3. HNO3 is an acid. It's a nitric acid. Remember that anytime you have hydrogen present in front, it's always going to be an acid. Okay. Acid is something that generally for inorganic acids, for inorganic acids, hydrogen is written first or in front. So you can miss that now. So this is the acid. This is the acid, nitric acid. And when it releases the hydrogen ion, it gives you minus one hydrogen ion. So now you are left with the nitrate anion. So this is the conjugate base of H. Always it's of what? Where is that, anion coming from? So you have to put that. Okay, now let's look at this guy. Another one is H2O. H2O, fine. It is HOH. When HOH breaks up, gives away one hydrogen ion, then it liberates the OH ions. Okay, it gives away the OH ion. So it's the OH1 negative. Okay, so here we have the acid, water acting. Water is acting as an acid. So it's not like water is an acid. So water, H2O, acting as acid. So when H2O is acting as an acid, it gives you the OH ions minus the hydrogen ion. So therefore, OH ion is the conjugate base of H2O. Where is that OH ion coming from? It's coming from the this H2O. Okay, so here this is acting as an acid, then this guy becomes a conjugate base. So minus that one hydrogen ion. Okay, now another examples we can see is the, like for example, H2SO4. So this is the acid, sulfuric acid. Now when this gives, remember it's only one hydrogen ion minus one hydrogen ion. And so this is going to make you HSO4. One hydrogen ion is a positive, that when it's removed, it's left with one negative charge. So keep this in mind that whenever, where do I write this? whenever one hydrogen ion is released or removed, the remaining species, whatever it is, gains a negative charge. And so this is what happens when H2SO4, when one hydrogen ion is released, one negative charge comes. That's all. And so this becomes the conjugate base of H2SO4. Okay. Now let's look at something interesting. So you have HSO4 negative. Okay, HSO4 negative. When this one gets rid of one hydrogen ion, then you're left with SO4. It already had one negative charge. Now it has left one more hydrogen ion. So another one comes. So it is -2. So this is acting, although this is ionic in condition, it is acidic in nature. This particular species is acidic in nature. When -1 hydrogen ion, this becomes the sulfate ion, which is the conjugate base of HSO4 1 negative. Clear? All right, so that's the deal with every acid has a conjugate base and the differences of one hydrogen ion. Now let's look at some of the bases. Now we have, this was the acids. These are the acids. And here are the bases. Okay, now we have base is, for example, base, acting as a base. For example, let's do bromide ion. Okay, so bromide ion, this is basic in nature, obviously, because it does not have a hydrogen ion, so it has to be a base. So this is basic, and every base will have, so here you are adding, remember bases accept bases are going to accept the protons or hydrogen ions. So then it becomes HBr. Now what is HBr? HBr is acidic, but this is a conjugate acid of Br minus. Okay, let's look at another one. ClO4. Do you see a hydrogen ion anywhere? No. So this has to be basic. Okay. And when bases accept hydrogen ions, so they are all adding hydrogen ion, and this becomes HClO4, and that's it. When a hydrogen ion is added, the negative charge is reduced or nullified. Okay. So here you have, this becomes conjugate acid of ClO4 1 negative. Okay, so let me put this here. Whenever one hydrogen ion is accepted, the negative charge is reduced or nullified or vanished, or is nullified. All right. Now we have here the, let's look at another example of Cn minus. So you see, every time it's a basis, then it's not like there is no hydrogen ion. So Cn minus, again, this is acting as a base. So this is basic in nature, and you are adding a hydrogen ion, and this becomes HCN. And HCN is a conjugate acid of Cn minus. Okay, let's look at another one. NH3. Remember, here the hydrogen is there, but not in front. So this is acting as a base. This is basic. So here, I'll put here, hydrogen is not in front. Therefore, it is basic. Okay, so here, this is adding one more hydrogen ion plus one more hydrogen ion. So this becomes NH4 and a plus charge is added. Plus charge because there are 4 hydrogen ions. So whenever plus charge is accepted, the negative charge is nullified. And in the case of neutral molecules, a plus charge comes. In case of neutral species, when hydrogen ion is added, the species gains 1 plus charge. Okay, so this is what it becomes. This is the conjugate acid of NH3. Okay, let's look at a few more. This is basic in nature. HSO4, 1 negative. Okay. So this is, although hydrogen is written in front, but it has 1 negative charge also. So this is basic in nature. Okay, because of negative charge. Negative charge means electron rich. Okay, electron rich due to negative charge. And anything that is electron rich can give electrons. Okay, so in other words, now this is basic, and when you add 1 more hydrogen ion, and this becomes H2SO4, and this is the conjugate acid of HSO4, 1 negative. Okay, if I didn't miss anything. Yeah, so we will cover more of these, the conjugate acid-base pairs when we are doing that thing. So, but right now, I think I covered quite a bit. And if there's anything you guys want me to show you, then I will, ask. Don't be afraid to ask me. Okay. So just keep this in mind that the basis, everything that is basic, you are adding 1 hydrogen ion. And anything that is an acid you are releasing 1 hydrogen ion. And that makes the difference. Okay, so that's what it is. So we will continue. This is a big chapter. So just make sure that, start doing your homework. And if you have any questions, please don't afraid to ask me. Okay, all right, thank you. Bye-bye.